Thanks. So Joshua Brody, I'm a fifth-year PhD student at Dartmouth College, and I want to talk about a communication complexity problem. Avi's actually worked on it also. It's called multi-party pointer jumping. So I'm not sure how much all of you know about communication complexity, so I think I'm going to take the first 5 or 10 minutes of the talk just to give you guys a primer. If all of you know about it, feel free to just shout out to move on. I'm going too fast or too slow, that's fine. Multi-party communication games. What does it mean? You can think of a communication game as this kind of problem. Maybe there's a bunch of people in a room talking together, trying to compute something. And I don't know if you see these red numbers on their foreheads. That's the input to the problem they're trying to compute. This model that I'm going to consider today is actually called the number on the forehead model, exactly because of this. So if you see a bunch of people in the room and you've got a number on your forehead, everyone else has a number on their forehead, you can see almost all the inputs. You're only missing one piece of input that's on your forehead. I think if you want communication lower bounds, this is a pretty hard model to work with because almost everyone sees almost all the input. There's a lot of shared information. So intuitively, it should be easier to solve your communication problem than the number in the hand model, for instance, where everyone's got their own private information. So there's a lot of different flavors to communication complexity. I don't have time to go over all of them, so I'm just going to tell you the basic model here. You've got some input. It's split between k different players. You want to compute some function on the input. Our model, like I just told you, is going to be the number on the forehead model. So player I sees everything except for x sub I. We're also going to be talking about one-way communication. So you can think of the players speaking, standing in a line. First guy says one message, and then never says anything again. And people talk in this particular order. And the last guy's job is to output the answer. And finally, we're going to talk about a blackboard model of communication. So I'm not going to just send one message to the next guy in line. I'm going to shout it out, and everyone's going to be able to see it. So what is multi-party pointer jumping? I think there's 2 ways to think about it. There's sort of a graphical way to describe it and a functional way. I'm going to start with the graphical way. So you can think of it as a layered graph. There's going to be k minus 1 different layers, n vertices for each layer, and a start vertex. And the input to the graph is going to be a layer of edges from one layer of vertices to the next one. If you notice, every vertex here has exactly one pointer pointing out to somewhere in the next layer. And there's also going to be an n-bit string at the end. And your goal here is to start at the start vertex, follow these pointers to the last layer, and just output the bit that's labeled at this vertex. So this should be pretty easy to do if you have the bit string and all the pointers. But the thing is, we're going to divide up all this input and put it on people's foreheads. So the functional way of describing it, you can think of, forgot about this. The non-Boolean version, instead of just a bit string at the end, you're just going to have another layer of pointers. And rather than outputting a bit, you want to output the vertex number that you reach at. So the functional way of thinking about this, if you look at each particular layer of edges here, you can think about this as one particular function. And that's because if you mark all the vertices 1 through n, we've got one outgoing edge. So you can think of this as mapping 1 to 3, 2 to 4, etc. So in this situation, the formal way to define the input, you've got some number between 1 and n, a bunch of functions from n to n, and a bit string at the end. And you just want to output the bit that's indexed by the composition of these functions. So trivial upper bounds for this depends on the order in which you speak. If you've got any order except for the first player speaking to the second player and so on, you've got a very easy log n bit protocol. So how does that work? Basically, if player 1 isn't the guy speaking first, you can just tell player 1 what this pointer is, just shout it out. And then player 1 speaks, and he's got the entire graph, so he can just compute the output by himself. If you go in any order, even if player 1 speaks, but you flip some player I and player j, you can basically do the same thing. It's going to be a log n bit protocol. The only non-trivial ordering is when it's player 1 through player k. When I first saw this problem, I thought this was kind of weird and counterintuitive, because the first guy speaking has almost all the input. He's just missing this one particular pointer. But I think the problem is, because he doesn't know this pointer, it's sort of like he doesn't know which of this amazing massive information is important or interesting to the output. The trivial version in this one is n bits, and that's if you just tell the last player the bit string on his forehead, then he'll have the input. So from just a interesting problem kind of perspective, I think this is cool. There's an exponential separation. We don't actually fully know the answer yet, but we think that there should be maybe a polynomial lower bound for this. Maybe not n, but maybe square root n, or n to the 0.001. So why do we care about this? The original motive, yes?
So this is the best upper bound, or this is the trivial one?
No, it is no longer the best upper bound because of a paper that I wrote with my advisor that I will tell you about in 10 minutes.
By the way, the trivial thing is n or n log n?
The trivial thing is n. So, yeah. So the input on the last player's forehead is an n-bit string. He doesn't have pointers. He's just got these bits, and there's n bits of them. So what we can do is have no one talk until player k minus 1. Player k minus 1 can say, player k, here's the input on your forehead. And then the last player has the entire input, so he can just compute the answer by himself. In the non-Boolean version, when you've got another layer of pointers here, the trivial upper bound then would be n log n. And it's essentially the best thing you can do is just tell one player what's on his forehead. That's the trivial upper bounds. Russell?
There was also an improved upper bound by Pudlak and Segal, I think.
Pudlak, Rodel, and Segal. Yeah. And this is, I will mention it, yes.
Okay,
yeah. This is an upper bound, but only when the functions are permutations instead of general functions. Let me talk about the motivation a little bit. The original motivation for this particular problem is in circuit complexity. Specifically, we've got ACC0. It's the class of all polynomial size, constant depth circuits with and, or, I believe not, and mod m gates. And the reason why this function matters is because we don't know any explicit function which is known to lie outside of ACC0. We know by counting arguments there are some functions, but we don't know of an explicit one. But there was a long chain of research in the early 90s that ended by showing that if you can take a function with k players for polylogarithmic number of players and prove a super polylogarithmic lower bound, that's sufficient to show that it's outside of ACC0. And we think that multi-party pointer jumping is a good candidate for that. So that's the original motivation. Later on, though, people have used this to prove lower bounds for a lot of different things, all sorts of different things, in fact. Not all of them have been like this specific version of pointer jumping. There's a lot of different versions, but it's been proved. It's been found quite useful to prove lower bounds in all sorts of different areas. So I think at this point, pointer jumping itself has sort of become one of the canonical communication complexity problems, similar to set disjointness or equality, that you want in your toolkit for proving lower bounds in other areas. So here's what we know so far. Like I said, we're far from this, holy grail end result that we want of proving that multi-party pointer jumping is outside of ACC0. But we do have some lower bounds. Specifically for 3 players, Avi proved a square root n lower bound. And this was generalized by Avi and Emanuela Viola, I believe here at IAS when he was a postdoc. to k players. And this n to the 1 over k minus 1, it's square root n for 3 players, cube root n for 4 players, etc. So it's a really good lower bound. It's the best we know so far. But it breaks down when we get into the k equals log n range. It becomes a not interesting lower bound for that amount of players.
Is there, by the way, for ACC0, you can even consider even more restricted protocols, right? Where simultaneous messages.
Yeah. So
We don't know how to use that to get better low bounds.
exactly. So what he's saying, there's a more restrictive kind of protocol than this one-way version called Simultaneous Protocols, where all k players send one single message to some referee who takes all these messages and combines them and outputs the answer. It's a more restrictive protocol, so the lower bound should be easier there. And a lower bound in that setting is sufficient for this ACC0 result, like you mentioned. Also, like you mentioned, it seems like we have more tools in our arsenal for proving lower bounds for this one-way communication, which is why that's what I'm going to talk about today. Usually, I wouldn't mention it just because there's just 80 different variants or flavors of communication complexity. I didn't want to overcomplicate things, but since you know about it, there you go. So in addition to these general lower bounds, there's been some lower bounds for some certain restricted kind of protocols, which I'll talk about later also. On the upper bound side, there's a non-trivial protocol by Tame, Yukna, and Segal for the non-Boolean version. Like I said, this trivial upper bound is n log n. This is an iterated log function. So for 3 players, we get a n log n bit protocol. For 4 players, it goes down. And for k bigger than log star n, this is a big O of n. It's a linear upper bound. So it's always within a log factor of the trivial upper bound, but it is non-trivial. And like Russell mentioned, Pudlak, Rodel, and Segal about 10, 12 years ago proved a slightly sublinear bound. It's log n over log n for the 3-person version when the middle layer is a permutation instead of a general function. So if you think about it graphically, how does a permutation differ from a function? All these pointers that we're looking at point to different things on the next layer. Intuitively, one would think that this is the hard case. And we don't know if it's hard or not because we've still got a big gap between the upper and lower bounds. But if you think about it, all these pointers point to different things. If they all pointed to the same thing, then there would be less information here. So I have 2 papers in this area. The first is this is the first non-trivial sublinear upper bound for the Boolean version. It's slightly sublinear. I think the most important thing is that it's little o of n here. And I've got some lower bounds in complexity this past year for certain restricted kinds of protocols. I'm going to tell you all about them in the second half of the talk. We don't really need their definitions right now. So for the rest of the talk, I'm going to spend maybe 20 minutes or half hour surveying the known upper bounds, including this one by Pudlak, Rodel, and Segal. And then I'm going to talk about these restricted kind of protocols and my paper from complexity. And finally, I'll talk about the conclusions and what the important open problems are in this area. So the first protocol I want to talk about is the Tame, Yukna, Segal protocol. Remember, this is for the non-Boolean version. So our output is going to be log n bits. It's going to be something between 1 and n. The trivial upper bound is n log n bits. And here's how the protocol works. We're going to start with player 1. He doesn't see this one particular pointer, but he's got these 2 functions. And what he's going to do is say, I don't know what this particular pointer is, so I'm going to reveal some bits of every possible one of the pointers in the second layer. So you could think of this as him giving the most significant bits or any arbitrary bits. Another way of thinking about it is taking the vertices in this layer and just dividing them into buckets, evenly spaced, n log n vertices per bucket. And then player 1 is just going to say, rather than what f2 of I is, he's just going to say what bucket f2 of I points to. Yeah, log n, sorry. So what's player 2 going to do? He sees this first pointer, green, and from player 1's message, he knows what bucket this guy points to. But he doesn't know within the bucket exactly where he points. But that's OK. He's going to take every pointer that's coming out of this bucket and reveal the answer for all of these guys. And since there are only so many vertices in each bucket, he's going to be able to efficiently tell the complete answer for all the possible things in this bucket. So he's going to say f3 of j for every possible j in this bucket. And player 3, he sees the first pointer and the middle layer. So he knows which bucket this guy belongs to, or exactly which vertex he wants. And he can recover the answer from player 2's message there. So how much does this cost? Player 1 is sending log n bits about n different things. And player 2 is sending log n bits about n divided by this number, which is actually n divided by log n. So the total communication is n log n bits. That's for 3 players. That's how the protocol works. For k players, it works exactly the same way. But because we have more layers, the first guy can afford to send less information about each pointer. He's just going to give the second player just a little bit of information. Second player is going to send a few more bits about a few smaller pointers, and so on. And you're going to end up getting that this iterated log thing, log to the k minus 1, is the answer you want. So the total communication here, like I claimed, was big O of n times this iterated log term. One other thing to mention here, can we use this method to get below n bits? Probably not, because we need to send information about every single one of these n different things. So second protocol I want to talk about is for the Boolean version. Pudlak, Rodel, and Segal. It's for a 3-player version, but only when the middle layer is a permutation. So all of these pointers have to point to different things. I think this is probably the, in terms of upper bounds, like this is the coolest upper bound. Here's how it starts. You're going to generate a random bipartite graph H. This is really just a, it's an existence proof, so it's a probabilistic argument. It is a deterministic protocol. We're just going to end up showing that a good H ends up existing. But for now, just think about it as a random graph. And it's going to be a bipartite graph between both these edges. So player 1, what's he going to do? He sees the red layer of edges and the blue layer here.
What's the degree of this bipartite graph?
I don't remember. I think it's like it's definitely little o of 1. I think it's something like 1 over log n.
Like n over log n? Like
Yes, yeah. So you're flipping a coin, and each edge is there with probability roughly 1 over log n. So you get n over log n eventually. So what's player 1 going to do? He's going to take this blue layer of vertices and this red layer, and he's going to create a graph on this second layer of vertices here. And he's going to put an edge in the graph if there's 2 particular edges in H. This is a little bit hard to see from this graph, so I'm going to reduce it a little bit. So here's what's happening. Take any 2 vertices here and go back along the red edges. And if you've got these 2 blue edges in your graph H, then you're going to create this AB edge in this new graph. Why would you do that? I'll tell you in a second. But trust me for now, this is what he does. And he's going to do this for all possible things. He's going to create these edges when he can. And he's going to end up having this graph that depends on pi on these vertices. Once he has this graph, he's going to create a click cover for this. So every component is going to be a click in this graph. And for each click, he's going to take the vertices there and the bits, and he's going to XOR all these bits together and then send the XOR, or the parity, of each one of these clicks in the click cover. Let's go on to player 2 now. Player 2 is much simpler. He's going to look at this pointer, look at the graph H, and for every one of the neighbors of this vertex in the blue graph, he's just going to send those bits in the clear. So basically, he's going to send this bit, and this bit, and that's it. So the magic for this comes out in how player 3 takes these two separate messages and ends up reconstructing the actual important bit that he wants. So here's what player 3 does. Remember, he sees this layer. He sees the layer here, this function, this layer of pointers, but he's missing this bit vector. What he really wants to do is recover this particular bit. So what he's going to do, he's going to take the click that contains pi of I, which is the vertex that he reaches by following the first two pointers. And let's look at this click for a second. Let's say there's some other vertex that's not pi of I that is in this click. We know because it's a click that there must be a j to pi of I edge here. And if there is such an edge in this graph H, then we know that player 2 sent this bit in the clear. So what does player 3 have? He's got the parity of a bunch of clicks.
Not clicks, the vertices. Parities of vertices.
Yeah. Okay. So you've got a click. It's got a bunch of vertices. And there's bits attached to these vertices. He's got the parity of all those bits together. And for every one of those vertices that's not the answer, we know that player 2 sent the bit that's attached to it. So all player 3 needs to do is take this parity, XOR out all the guys that aren't pi of I, and what's left is the bit that he actually wants.
What's the size of the click?
That's a good question. I don't actually know the size of the clicks. We know the number of clicks, which is the important part. And if you do the analysis, it's a probabilistic method argument, you end up getting that there exists a graph H that works for all I and all pi, such that g of h, this graph that you get, ends up having like n log n divided by log n clicks. And each yi has out degree n log n divided by log n. And for the communication cost, that's the important part. Player 1 is going to send 1 bit for each of these clicks. Player 2 is going to send 1 bit for each of these neighbors. And that's how you get the answer to the protocol. When I first saw this just seemed like sort of like black magic to me. The analysis is sort of just basic probabilistic method. H is just a random graph. Every edge is just probability p. But determining that this is the right number of clicks really relies on some graph coloring results that Balobash did in the 80s. What's that?
Using martingale arguments? Or?
I don't know.
I'm not sure you made it. I don't think this
So the use of the fact that you have permutations is in counting or for the union bound, or is it something?
Yeah, so that's a good question. And I think it's basically the union bound. So, if there's some other function, you could still take this random graph, right? And, you could still create this graph g pi.
The out degree will be a problem if it's not. The out degree will be a problem.
Is there a probabilistic protocols that are, this will give you like a probabilistic protocol if what you're saying is
No. They all know this graph exists.
Graph is
so-
fixed
No,
and it's
but
good
he
for
says
all
that-
permutations.
No, but he says that if it wasn't permutation, you would still get a probabilistic protocol. So I wonder if there are better probabilistic protocols now. I mean, maybe this is not true, but he said that the only problem is the
Yeah. So
you still get a probabilistic protocol even if pi wasn't a permutation.
No. Yeah, I think that actually is true. Will you get a good probabilistic protocol? How much will your error be? How often will you make a mistake? I have no idea.
And are there better probabilistic protocols known?
I don't think so.
No. In general, this is sort of a tangent, but most of the known upper bounds for this are deterministic. Most of the known lower bounds are randomized. I don't know. My intuition is that there is actually a good reason for that. I don't think randomization is going to help you in this problem.
So randomized means shared randomness?
Yeah, typically. Yeah. For this problem, when I think of randomized protocols mentally, I actually really think of distributional protocols where there's some input distribution and I'm allowed to make a epsilon fraction of mistakes. Yeah, but randomized protocols.
Can you go back
Yeah.
to the protocol? So the click cover is defined on the original graph, not the graph plus the edges, or
Yeah.
Right.
So the click cover is defined on this.
Okay, and G is defined by both the original graph and the new edges and the permutation.
Yes. So G is a function of H, this random graph, and our permutation here.
Non-trivial use of this intersection of information like this stuff.
Are there any other questions right now? Okay. So the final upper bound I'm going to give is one I wrote with Amit Chakrabarty, my advisor. And the general idea is to take this Pudlak-Rodel-Segal protocol. It works whenever we've got a permutation in the middle. And we're going to try to run it a bunch of times in parallel. And what I want to do is I want to pick my permutations carefully such that no matter what I is, there's some permutation in my list which matches F for that particular I.
What do you mean permutation? The input is given.
The input is a function.
The function. So
Yeah, I want to run the Pudlak-Rodel-Segal protocol for a bunch of different permutations
that you
That will
derive
cover.
from the function.
To somehow cover the function.
Exactly. So that's how I think about it, actually. I'm going to say pi covers I if pi of I equals f of I. And if pi of I equals f of I, we can just run the Pudlak-Rodel-Segal protocol for pi, and we're going to output the exact same answer. So that's the idea. We're going to try to get a bunch of different permutations and run them in parallel. And the idea is, we want to cover each of the red pointers, each of the functions, with some pointer that's in one of these permutations. And if we can do that, then player 3, player 1 and player 2 are going to run the Pudlak-Rodel-Segal protocol a bunch of times in parallel. Player 3 can pick out the permutation that actually gives you the right answer, and that's the only version of the protocol that he's going to care about.
And you handle those that have very high degrees separately.
Yeah. That's the secret answer at the end. So where does this break down? It turns out that this works. It's going to work, just like you said. The problem is that you might need a bunch of different permutations. And the degree is actually exactly where this breaks down. So if you look about it, think of this function. Imagine if it was a constant function. So all the pointers are pointing to the same thing. If it's constant, then we'd actually need a different permutation for each one of these pointers. And that's like way too many permutations. That'll blow up our communication cost by a factor of n, which is ridiculous. But that turns out to be the only problem here. So technical details. I'm going to say we've got a set of permutations, and it's going to decover f if for all these indices, either we have some permutation that covers it in our list, or f of I has a large preimage. And by a large preimage, I mean exactly this. Like, we've got a bunch of pointers that are coming into it. It turns out that that's the only roadblock that's standing in our way. It's pretty easy to show that for every f, you can find this decovering set. It's deterministically. And note that if you've got a point with a lot of preimage, you can't have too many of these points because the preimages are disjoint. So we can't have too many of these. And player 1 sees this middle function, so he knows which guys have large preimages. So he's just going to send the answer for those points directly in the clear. And that's what happens with this protocol. So player 1 is going to send a bunch of copies of his message for the Pudlak-Rodel-Segal protocol and a bunch of bits in the clear. Player 2 is blissfully unaware of what's going on. He's just going to follow the Pudlak-Rodel-Segal protocol a bunch of times. And that gives player 3 enough information to recover the answer. So the appropriate setting for D here is the geometric mean between n and the Pudlak-Rodel-Segal protocol. So that's where you get n square root log n divided by log n. If you end up having a better protocol for MPJ3, when it works for permutations, you automatically get a better general protocol.
So this is kind of a proof that what you said before, that permutation is the hardest case.
Yeah, exactly. Like, I mean, technically, maybe it's easier. Log n over log n. Can't be that much easier. Yeah.
Probably I didn't calculate, but if you had a polylogarithmic protocol for permutations, you'll get a polylogarithmic here as well, or no?
Should be square root. Right?
We'll get it through that.
Should be square root, geometric mean. Yeah. So we also, in this paper, we also have even slightly better upper bounds for more k than 3. But they're only slightly better. It's this square root n is like n to the 2/3 or 1/3 or something. I think the important part of this result is not even this term. I think the important part is that it's just little o of n. So in a way, this upper bound is actually an impossibility result because the goal here was to show strong lower bounds. So I think other people might have other opinions, but I think the conventional wisdom at the time, certainly my advisor thought so, that omega n, or maybe omega n over k or n over poly k was the right lower bound for this. So this sort of was a surprising disproof of that.
So what's log between friends?
What's that?
What's log between friends?
Yeah, exactly.
Are there other communication complexity problems where the answer is n for k for any constant k?
I'm sure there are.
Generalized inner product.
Generalized inner product.
Okay, so yeah, so the next thing I want to talk about is these.
But these protocols, by the way, they do use. I mean, just to be, you still have this property that player. It uses the fact that they are talking in order. It's not a simultaneous message protocol, right?
That's correct. Although
So it might be that for simultaneous message, the answer is still A.
yes, yeah. And in fact, for these particular protocols, they're what's called almost simultaneous message, because player 1 could equivalently just send his message directly to player 3. Player 2 never looks at his message. It's just a function of his input. So it's sort of a halfway between one-way and simultaneous message. So player 3 receives a message from player 1 and player 2 and looks at his input and outputs the answer. So it's sort of halfway in between. So now I want to talk about these restricted protocols. I think part of the motivation for looking at restricting what kind of protocols you can do is that just proving a lower bound that's better than square root n for 3 players just seems really hard. So we're going to try to find some restrictions on the protocol and say something interesting about them. I think these are both very natural. I know I've talked to Emmanuel about it. He thinks that they're ridiculously unnatural. But his result was for general protocols, so there was some incentive to think that. Anyway, myopic protocols. Myopic means short-sighted, so basically think of these players in a line, or you can think of the graph if you want. Myopic protocols, every player sees all of the layers behind him, but rather than seeing all the layers ahead, he just sees what's on the next guy's forehead. So 2 guys away, he doesn't see the input on his forehead. A conservative protocol restricts the input that you see behind you. So in a conservative protocol, you see everything ahead of you, but rather than seeing the j-1 layers behind you, you basically see the answer you would get if you follow the first so many pointers to the vertex layer that's right before your input. So you end up getting another index, but it's an index that points directly to the vertex layer that's right before the input on your forehead. So why do people care about these? If you remember the Segal protocol, it was actually both myopic and conservative. So these seem quite restrictive, but until our paper last year, there wasn't a non-trivial upper bound for the Boolean version. The only non-trivial upper bound used both of these guys. So the goal here was to prove lower bounds in these restricted protocols. There have been a couple different papers. Segal gave a lower bound for conservative protocols. Gronemeyer gave a weak lower bound for myopic protocols. The state of the art, it was in a paper in complexity by Amit, and he gave randomized lower bounds, n over k for myopic, n over k squared for conservative. So in the non-Boolean version, you can do something smart with these guys. In the Boolean version, this is very close to the trivial upper bound. So the question I wanted to ask here, I'm going to talk about myopic protocols only for the rest of the talk. And whenever I say protocol, I really mean myopic protocol. The question I wanted to ask here was, we've got this myopic protocol that's good for the non-Boolean version. And the only difference between the non-Boolean and the Boolean version is this last layer of inputs. So why can't we have a myopic protocol for the Boolean version? So I wanted to ask this. Can we get any non-trivial myopic protocol?
No, I'm confused. Didn't Chakrabarty show that you can't?
Chakrabarty showed n over k. So
trivial,
yeah. So I will admit, maybe you can do something slightly non-trivial, but Chakrabarty showed that you can't do something that's like much better. But can you get anything that's better than n? Can you get like an n-1 bit protocol that's myopic? I just want anything non-trivial. And it turns out the answer is no. Myopic protocols, the best you can do is n. It's not even n-1 bits. It's an exact bound. But it's actually more interesting than that. I'm going to look at actually the maximum communication. It turns out that in any myopic protocol, not only do you need to send n over 2 bits, but it's basically one player that has to send almost all the information. So some player must send at least n over 2 bits. And this is totally independent of k. So k could be exponential in n, and you'd still need some guy who has to send almost all the information. So a little bit of notation. We're going to start talking about maximum communication now instead of total communication. So when I say the cost of the protocol, I just mean the maximum communication. It's the cost of the largest message. Total cost, I'm going to say, is t cost now. And whenever I mean a delta n-bit protocol, I'm talking about max communication. So the main theorem that I have in this paper in last year's complexity, in its more detailed version, it actually does depend on the number of players, but not by much. So there's some decreasing function on the number of players that never gets to 1/2, such that any deterministic protocol has to communicate at least this many bits, max communication. The only reason why I say it in this detailed form is because I actually have a matching upper bound also. And it's not just asymptotically matching. I get the constant right. This constant is actually, in general, irrational. But despite that, we give a max communication protocol that matches it up to second order terms. So secondary results in this paper. I already mentioned the first one. If you dig into the proof of this and pay attention to the total communication instead of the max communication, you get this n-bit lower bound. So it's an exact lower bound. You can also apply my proof technique for this to the non-Boolean version, and you get a deterministic lower bound which matches the Segal protocol, again up to a second order additive term. And finally, you can randomize this. You end up getting a n over k log n. Now, this randomized lower bound from emit was n over k. That's for total communication. If you look at max communication, you lose another factor of k. So we have n over k squared versus n over k log n. For the number of players that we care about, mine's slightly better. But it is like not the most important result here. It's the deterministic upper and lower bound, which really matters for this problem. So I think in the 15 minutes I have left, I'm going to prove the lower bound on the main theorem and try to sketch other stuff. Yes?
So just to make sure I'm following. So the upper bound that you gave is better than the lower bound for Myopic protocols. It's for the same problem?
The upper bound that I gave was not myopic.
Right. So you're saying the best protocol really can't be myopic?
Yes.
Among other things.
Yeah. Yeah, and for 3 players, what does it mean to be not myopic? What player is one message? It has to really depend on both layers of input that he sees. So here's what I'm going to do. The main technique I use here is a combinatorial hook plus a round elimination lemma. I assume most of you have probably at least heard of what a round elimination lemma is before. If not, don't worry about it. I think it's a fancy way of saying induction sometimes. What you want to do is you want to take a 2-player protocol and say, it's really simple. We know that you need this much lower bound. Then you want to say, if I have a nice k-player protocol, I can get a nice k-1 player protocol. And that's the round elimination. You chain these round elimination lemmas together, you get a nice 2-player protocol, which you know by your base case lemma can't happen. So I think in general, when you're talking about round elimination, sometimes in general, like what you really need to do is think hard about what you mean by a nice protocol. And that requires thinking outside the box sometimes. I think the general lower bound of Viola and Vigderson, for instance, was also a round elimination. And they had to generalize the protocol. For me, all I have to do is just think a baby step outside the box. It's just a small generalization. And I'm going to add this parameter m. And all it is I'm going to pay attention to the number of vertices in the first layer. So rather than n vertices, I'm just going to have m. That's the only generalization I need to make. And the high-level idea of this round elimination is we're going to pop off 1 layer every round. And I'm going to shrink the number of vertices in the first layer as I'm doing this. And the goal is, I want to get down to a 2-person protocol, but still have a bunch of vertices in the first layer. And that's how I'm going to get the lower bound. So here's the setup. The base case lemma is really easy. It's just the index problem. Alice has an array. Bob has I. You want to output x sub I. It's been well known that Alice basically needs to send the entire array to do this. Here's the round elimination statement of the lemma. If I've got some protocol for the k-person version, then I've got a protocol for the k-1 person version with the exact same cost and with this value of m prime. And trust me, this value of m prime is less than m. We're going to see it in the analysis in a second. But for now, just think m prime is less than m. And if this delta n scares you, just think of delta as a half n over 2. So here's the setup for my round elimination lemma. The high-level idea here is that player 1's message partitions his input space. So what does he see? He sees just what's on player 2's far head. It's a function. So these functions, the input space is n to the m. And I'm going to say that this set m is a message set. It's the set of all inputs that he would send this particular message on it. And what I'm going to do in the round elimination lemma is I'm going to fix the first player's message just to maximize this size. Now I've got a quick combinatorial hook, which I call the range. And all it is you take a family of functions and a particular I, and just look at where all these functions map this particular I. And that's it. So if you look at the range, intuitively, if this size of this family function is large, then we should have a large range. Maybe we don't have a large range for all I, but there should be some I that has a large range. And that turns out to be true for every family of functions with this size. There must be at least one I with range at least m prime. And that's going to be all we really need for the round elimination lemma. So here's the proof. We're going to fix m, like I said. If you crunch some numbers, you end up getting the lower bound of m prime to the m, which is exactly what we need. So by the range lemma, we know that there's some...
What will m prime be?
M prime is n times 2 to the minus delta n over m. And I'll work through the math a little more explicitly.
But we should think of m prime as a constant function of m.
Close to a constant, yeah. And we should think about it as just slightly less than m.
Yeah, it's better than a constant function. It's something very close to 1, I guess.
If it's a constant function of m rather than n, it's very close to 1. Yeah.
Right. So as m goes down, you get a bigger and bigger chunk of m prime will be closer to m.
Yes. Yeah. M prime will be closer to m as m goes down. Yeah.
That's why you never get below a half.
Yes. That's why you never get below a half. You get this decreasing function. Yeah. So where was I? We've got this range lemma. We know there's some I with large range. So we're going to fix that I now. So we've now fixed the message, first message, and we fixed I. And for each j in this range, we're just going to fix some function in our message set which maps I to j. And we know we can do that exactly by definition of what range is. And the only thing protocol Q does is rather than having j and the rest of the inputs, he's going to pretend that he's in a k-person protocol with I and this special function gj. But we know that gj maps I to j. So the answer for the k-person version is going to be exactly the same as the k-1 version. Exactly the same. And we know because we fixed the first person's message that we have one less message. So that's the round elimination. So let's go through the analysis a little bit here. I'm going to define sequence of numbers in terms of this delta. And remember, eventually we want delta to be at least a half, or to be at least this decreasing function. So a sub 0 starts at 0. A sub L is delta times 2 to the last guy, a sub L minus 1. And m sub L is going to be n times 2 to the minus a sub L. So these a's look like this. So a0 is 0. A1 is delta. And we end up getting this tower of deltas and 2 to the deltas. And I'm going to define phi of k to be the least delta such that this guy is at least 1. So based on delta, we know what this a sub L is going to be. It's not too hard to show by induction that this is a decreasing function and its limit is a half. And if you go back to what I said in the round elimination lemma, but you start with m sub L, m prime is n times 2 to the minus delta n over m sub L. If you go through the math, you get exactly m sub L plus 1, which is what we want. So we're going to start the round elimination lemma with k players and m sub 0, which is exactly equal to n. That's the original pointer jumping problem that we want to solve. And when we pop off one player, we go from m sub l to m sub l plus 1. So what we end up getting for the main theorem, definitely ask questions. I think everyone here knows what's going on in this paper. This is pretty basic communication complexity. You start with a delta n-bit protocol. You do a bunch of round eliminations, and you end up with a protocol with the same cost, but with m sub k minus 2 vertices and only 2 players. So by the base case lemma, we know that this has to cost at least m sub k minus 2. So we've got delta n is at least this. If you crunch the numbers, you get that a sub k minus 1 is at least 1. So by definition of our choice of 5k, this is what we get. OK. I've got maybe 5 more minutes. I'm going to sketch the upper bound. Once I had this lower bound, it seemed pretty strong. Amit was like, you should think about these things, and it'll improve the paper. And it turns out the proof technique I used for this, generalizing it to this, where we're shrinking the number of vertices in the first layer, it, I think, essentially exactly captures what's going on in pointer jumping, at least for myopic protocols. So the idea here is I'm going to cover the input space with sets that sort of have maximal range. And by that I mean that for every single I, the range is exactly m prime. So you can look at the set of all possible sets for this. Just by a volume argument, we know that we need at least 2 to the delta n sets to cover the whole input space. But if you take a bunch of these at random, just work through week 1 of the probabilistic method, it turns out that you need roughly 2 to the delta n plus little o of n. And this is going to be the communication cost. So the protocol, player 1 is going to look at his input. It's a function. And he's going to look for the set that covers that contains it. And he's just going to tell player 2, this is the set that contains my input. The rest of the players are going to see I. They're going to fix the range. And now they've got a k minus 1 person protocol. Yeah, S is one of these sets. I don't know what this covering set is, but I know that there's, at most this many guys that cover the whole input space. And then they can set the range and just do a k minus 1 person protocol on a reduced version. And so this upper bound actually exactly matches what's going on in the round elimination. And so that's where you get the matching upper bound. Randomizing the lower bound is actually also pretty simple. The statement is almost exactly the same. The m prime parameter changes by just an almost insignificant amount. The only real thing that changes is this error term here. And it goes up by a factor of 2 to the n. And here's where I lose the error parameter. By the way, this is a distributional complexity lower bound. I'm assuming you've got deterministic protocols. The input distribution is uniform, and you're making an epsilon fraction of errors. So just say z is the rest of the input. That's not the first 2 guys. And we're going to call I and F2 bad if the probability that we make an error in the protocol given these first 2 inputs is at least 2n epsilon. And we're going to call F2 bad if it's bad if I and F2 are likely to be bad. So just by averaging arguments, you can show that just by 2 Markov inequalities, we're going to end up finding out that at least half of the F2s are good. And the trick here is think about what it means if F2 is good. It means that the probability that I and F2 are bad are strictly less than 1 over n. But there's only n different choices for I, so that probability is actually 0. And we end up getting that F2 is good implies that I and F2 are good for all I. And now we're at the setting where we can use just a deterministic argument. But we're only going to pay attention to good Fs and good I and F2s. And you're going to do the exact same reduction, and you end up getting a protocol with error guarantee at most 2n epsilon. So you get a blow up of 2n. If you apply this roughly k times, you get a blow up of roughly n to the k. So you lose a little bit of juice here because you have to drive the error down using standard error reduction techniques at the beginning. And you lose a factor that's logarithmic in this error blow up. So log of n to the k is k log n. And that's where the lower bound comes in. So that's about it. Conclusions, open problems. This deterministic complexity, even for just 3 players, it's still pretty annoying. By annoying, I really mean fascinating how far different they are. We've got this root n lower bound. Now we've got something that's slightly sublinear, but we don't know anything more than that. This myopic protocols, some people care about it, some people don't. I think my paper sort of, yeah, just for 3 parties. So myopic communication complexity, we have a very, very good understanding of exactly what you can and cannot do with them. This lower bound technique, round elimination plus combinatorics, it's pretty old school. But I think this, if anything, this paper I think is actually a good illustration that it's still a useful technique. I was actually pretty surprised that you could use round elimination at all and get n over 2 lower bound, independent of the number of players. I think it's a little bit surprising that you can get a lower bound that gets the constant right also. So I think it's a good technique that you should have in your toolkit if you're doing communication complexity. Open problems, this is the holy grail. It's a good result if you can figure out exactly the deterministic complexity. Like you said, like someone said, simultaneous message, that's fine too. Just go with that if that's what gets you the result. When I think about the problem now, I usually don't even think about anything more than 3 players, because there's still a big gap with 3 players. And I have a feeling that if you can improve the lower bound for 3 players, you'll be able to improve the lower bound for general players also. Just 1 minute. I'll talk about a little bit about this lower bound. It's all Avi's work, so he could tell you more about it. But basically, you end up dividing the input space into sort of a d-ary tree structure. So for 3 players, the first index only has root n choices. And wherever it goes, all those guys only have root n choices. And by making the pointers downstream sort of all disjoint from each other, you can get sort of a direct sum kind of argument where the first player does need to say a little bit about every single one of these subtrees. The reason why I say that now is because I think that's where the lower bound barrier is right now. You get this root n thing, and it's going to be really hard to break above root n because of this tree structure. So it's I don't know, annoying, fascinating, take your pick. It's usually when I think about problems like this enough, and I get this lower bound, and I can't improve the lower bound, I would like to think that the reason why I can't improve it is because it tells me something about what the upper bound should be. I think in this case, I think this root n lower bound, I have a feeling it doesn't tell you anything about what the upper bound should be. So even if you can get like root n log n lower bound, that would be cool. So I guess that's it.
All right. Thanks again.
Thanks.